Security Analysis of Agentic AI Communication Protocols, a comparative evaluation.
This paper analyzes the security of agent communication protocols. It reports a distinct gap between one protocol's architectural design and the security of its public implementation.
So we'll start with the communication problem itself, then cover the framework used for assessing vulnerabilities. After that, we'll get into the protocol evaluation, compare architecture versus implementation, and then finish up with some recommendations.
All right, let's start with the agent communication problem. What are the specific security challenges here? How does agent-to-agent communication differ from a traditional client-server model?
Well, standard security models don't really fit. With agentic systems, you're managing peer-to-peer trust and dynamic task delegation. This introduces risks like credential leakage and unverified execution, where one agent might execute a command from another without the proper checks.
And which specific protocols were evaluated in this work?
3 protocols were compared. First is A2A, which uses OAuth and JWT, a common model for web services. Then there's Coral, which uses decentralized identifiers and blockchain wallets for a more distributed system. And finally, ACP, which can use bearer tokens or mutual TLS. Each has different architectural weaknesses.
The analysis is based on a semi-trusted environment. It assumes an adversary can intercept network traffic and replay tokens. The adversary's goals are straightforward: data exfiltration, message tampering, or denial of service. Okay, let's look at the framework used. How was the security analysis structured to ensure a systematic comparison across these different protocols? A 14-point taxonomy was used, and it's organized into 5 domains. You have authentication for proving identity, authorization for controlling permissions, data integrity to prevent tampering, confidentiality for keeping information private, and finally, availability to ensure the system is operational.
So let's get into the empirical results. What did the actual tests reveal about the security of the Coral implementation?
A critical authentication flaw was found. The official Coral implementation is vulnerable because it fails to validate the primary credential on its server-sent events, or SSE, endpoint. SSE is the technology that lets a server push data to a client.
And the paper is very specific about this. In 50 out of 50 trials, an attacker could connect to a session's event stream using only a correct session ID. The private key check was bypassed entirely.
Were similar flaws found in its access control mechanisms?
Yes, the tests also identified an authorization bypass. The Coral server did not reject connections from clients that were using fabricated agent identifiers, ones that were not part of the session's verified participant list.
Did the testing validate any of Coral's intended security strengths at all?
It did. The implementation showed robust message integrity and session isolation. All attempts to tamper with messages were rejected. But on the other hand, it had a denial of service vulnerability because of a complete lack of rate limiting.
So when you consolidate all these results, what's the overall picture?
The final matrix shows a pretty clear pattern. A2A is vulnerable in most categories. ACP security is partial and depends on how it's configured. Coral shows strong integrity and confidentiality, but is vulnerable in authentication and authorization due to those implementation flaws.
The paper computes an exposure score where a lower score is better. Now, Coral actually scores lowest at 7.0, followed by ACP at 9.0 and A2A at 12.0. The catch is that Coral's low score hides those critical implementation failures. It's not just about the design weaknesses.
Right. So the central finding here is that a secure protocol design on paper doesn't guarantee a secure system in practice. The implementation details are what determines the actual security posture.
Given these findings, what does the paper propose as a path forward for building more resilient protocols?
The findings do seem to align with recent industry moves. The merger of A2A and ACP, for example, suggests their individual architectural flaws were recognized. Also, Google's new agent payment protocol validates Coral's design choice to integrate secure payments as a core architectural feature.
So the primary recommendation is to build a hybrid model. This would combine Coral's integrated architecture with the mandatory per-message integrity checks from ACP, like JSON Web Signatures, or JWS, which provides a way to verify a message hasn't been tampered with.
So this brings us to 5 actionable takeaways for developers. 1. Validate the implementation, not just the design document. 2. Mandate security features, don't make them optional. 3. Integrate secure payments as a core component. 4.
combine transport and message layer integrity checks. And 5. Conduct continuous adversarial testing.
And this leaves a final question for the field. How can the industry ensure that the security of a protocol's implementation consistently matches the strength of its architectural design?